Hi there. We talked today in class about particle motion, specifically as it relates to position, velocity, and acceleration. And this will be a popular topic on your free response of the AP test. It doesn't show up every year, but it is a common one. So on the front page of your notes, and these are uploaded to my website, we defined some terms as well as looked at some key words or key phrases that should elicit a certain understanding when you read them. So I have here them all filled in, and again, these will be uploaded to my website so that you can either write them down or print it off. Position is a location of an object, for example, a particle. We typically will use x of t if we're moving horizontally, y of t if we're moving vertically. Every once in a while you'll see like an s of t or something like that. And when we are discussing the position, we use a distance unit, for example 4 feet or 3 inches or 2 meters, something like that. Velocity, there are typically two types of velocity we'll be looking at, average velocity and instantaneous velocity. Average velocity is the change in position over the change in time, aka slope, because the relationship between velocity and position, as seen here in instantaneous velocity, is that velocity is the derivative of position. And so if our position was 3x squared, or was shown by the function 3x squared, our velocity would be 6x, because the derivative of 3x squared is 6x. And when we're talking about velocity, we'll use a distance over time unit, for example, feet per second, so 3 feet per second. One common thing that starts to happen occasionally is that students will mix velocity and speed, right? Because when you think of speed, you think of like 65 miles per hour. Velocity and speed are related, but they are not the same thing, and we'll look at that more on Monday. Acceleration then. Acceleration, same to average and instantaneous. Average is the change in velocity over change in time, which is, again, slope. And the reason is we see here in instantaneous velocity in instantaneous acceleration, is that acceleration is the derivative of velocity. And so if our velocity function, as we said above, our position function was that 3x squared, our velocity would then be 6x, which would make our acceleration the derivative of velocity, which is 6. And that's how they're related there. The reverse then is also true, right? If we take the integral of acceleration, we'll get velocity. The integral of velocity will get position. And when we're talking about acceleration, we use a distance over time squared unit. For example, 4 feet per second squared. The reason is because acceleration is velocity over time. Velocity is our meters per second. Time is seconds. Well, meters per second is the same thing as meters per second squared, which is why that would be our acceleration unit, a distance per time squared. Okay, and then we looked at these phrases. Within the context of a problem, if you saw the word initially, you'd be thinking, well, time t is 0. At the origin means the position is 0. At rest, our particle's not moving, so velocity is 0. Velocity, like I said, is different than speed because velocity has a directionality to it. Velocity is a vector, as opposed to speed, which is a measurement. Velocity is positive, or if velocity is positive, then the particle is moving to the right or up. If the velocity is negative, then the particle is moving left or down. Okay, to find average velocity over a time interval, we divide the change in position by the change in time. Again, velocity is the derivative of position, or slope of the tangent line of position, right? So if I'm looking at what's the average velocity from time t equals 1 to t equals 4, which are these 2 points, I'm essentially going to be calculating the slope between those 2 points. That'll give me my average velocity. So change in position over change in time. Position goes from 6 to 4, so 6 minus 4. Time goes from 4 to 1, 4 minus 1, which is 2/3 meters per minute. Okay, instantaneous velocity is a velocity at a single moment, right? So in our instance here where we had our position of 3x squared, our velocity, or I should say t actually, 3t squared, all of these should be t technically, right? Because we're doing v of t. Okay, so velocity is 3t squared, position is 3t squared, velocity is 6t, acceleration is 6. If I wanted to find the velocity at t equals 2, well then I'd find my derivative of position, 6t, and then I'd plug in 2, v of 2. And v of 2 would be 6 times 2, which would be 12, and then whatever our units were. All right, so instantaneous velocity is the velocity at a single moment. Okay, 8. If the acceleration of the particle is positive, then the velocity is increasing. If the acceleration of the particle is negative, then the velocity is decreasing. 10. In order for a particle to change direction, the velocity must change signs, right? Which again makes sense. If we have our x-axis here, and we have a particle, so this is 0, 1, 2, 3, negative 1, negative 2. We have our particle here that's moving right. The only way that it can change direction is for at some point it has to reach a point where it stops and then starts moving left again, which means our velocity is positive, 0, negative. Right? That's the only way our particle can change position, or vice versa. If it's going negative, so it's left, 0, positive. Right? That means our particle is going to be changing direction. So for a particle to change direction, the velocity must change sign. Then the last one here, if we're asked to find total distance, distance is a positive measurement, right? So we're going to be taking our integral from a to b, because the integral of velocity would give me position, which would allow me to calculate distance. So I'm going to be taking the total distance, a to b, but I'm going to do absolute value of velocity because I need it to be positive, right? I want the total distance. And so then we practiced it with this problem. We took our velocity, which was taking the derivative of this function, and then calculated what it was, which was 36. Okay? And so we have 3 practice problems here that we're going to work through: a numerical, a graphical, and an analytic one. Okay. And again, these are on my website. So we have the data in the table below gives selected values for the velocity in meters per minute of a particle moving along the x-axis. The velocity v is a differentiable function of time t. So then my table here gives time t and velocity v of t in minutes and meters per minute. Okay, when you see the word when you see the word differentiable, you know that this means that there aren't any cusps or any breaks, right? If we were to take the derivative of our velocity, we would be able to calculate that at every point. And we also know that it's continuous, because if it weren't continuous, then it wouldn't be differentiable. There would be a hole there, and we wouldn't be able to find the derivative at that point. Okay. So number 1 says, at t equals 0, is the particle moving to the right or to the left? Explain your answer. Well, at t equals 0, my velocity is -3. And since my velocity is negative, we have this on the front here, when velocity of a particle is negative, then the particle is moving to the left or down. Okay, so since we're at -3, our particle, the particle is moving left. Because v of 0 is negative. The velocity at t equals 0 is negative. Okay, number 2 says, is there a time during the time interval 0 to 12 minutes where the particle is at rest? Explain your answer. Okay, well, for our particle to be at rest, there has to be a spot, or to guarantee that the particle is at rest, we have to be able to see a change in direction, right? Where our particle was moving either right, so velocity was positive, and then stopped and started moving left, or vice versa, our particle is moving left, so the velocity is negative, and then stopped and started moving right. And so when we're looking at this table, that's what we're going to be looking for, is can we see in our particle's movement a change in direction? Because if there was a change of direction, well, the particle had to stop, right? Think about your car. If your car is driving forward down the road and you flip it into reverse, it's not just going to automatically start going backwards. It's going to have to stop so that the wheels can start turning the other direction. And that stop might not be for very long, but it had to stop, right? It had to slow down and reach a zero. Okay? So when I'm looking here, my velocity at -3, we already established was that our particle was moving left at t equals 0. Well, right here at t equals 2, now our particle is moving right. The only way that could happen is that somewhere in that interval our particle had to stop. Right? So is there a time where the particle is at rest? Yes. Because v of t changes sign. From negative to positive. And so then the other question that you would have to consider potentially would be, was there a break, right? Did it switch from negative to positive because there was a hole in our graph? Well, we already took care of that with this fact here. Velocity was differentiable and therefore continuous. So there's no way there was just a break in our graph. It had to hit 0, right? And since velocity is continuous, there had to be a point where v of t equals 0. Number 3, it says use the data from the table to find an approximation for v prime of 10. And I'm actually going to pause there because v prime of 10 makes me consider other relationships that might imply, right? V prime is the derivative of velocity. And as we discussed on the front page, the derivative of velocity is acceleration. And so I might jot that down for myself just in case it comes in handy, right? Maybe I want to know I'm finding acceleration. Well, the other thing it should elicit is, since it's v prime, the derivative of velocity, derivative means the slope at that point, right? The slope of the tangent line at that point, t equals 10. Okay, and so either of those relationships mightn't come in handy, but they're things we should be thinking to ourselves. As soon as you see that derivative, you should be thinking, oh, slope, got it, making that connection. And v prime is acceleration. X prime or y prime, whatever our position is, position derivative is velocity. Okay, so we're going to go ahead and calculate that, or approximate it technically, and explain the meaning in terms of the motion of the particle. We're going to show the computations that lead to our answer and indicate units of measure. Okay, so when I'm looking at my table up here, I know that t equals 10, which is what I'm trying to find, is right here, located halfway between t equals 8 and t equals 12, and what better place to be situated for finding an approximation, right? Right at the average, okay, between 8 and 12. Kind of mean between 8 and 12. Okay, and so I'm going to use these 2 points to calculate my approximation. And how am I going to do that? I'm going to use the fact that I know that v prime derivative is slope. And I know how to find slope. I've been doing that since algebra, right? Change in y over change in x. Or, as we discussed on the front, since it's acceleration, acceleration is the change in velocity over the change in time. Well, I have here 2 velocities. I can find their change, and 2 times. I can find their change. Okay, so that's what I'm going to do. Change in velocity over change in time. My velocity went from 7 to 5, and time went from 8 to 12. Right, 7 to 5, 8 to 12, which is 2 over negative 4, which is negative 1/2. And they want units of measure. Well, velocity is meters per minute, and time is minutes, which is another way of saying negative 1/2 meters per minute squared. And again, those units make sense because v prime, derivative of velocity, is acceleration, and acceleration's unit of measure is a distance over time squared. What does this mean in terms of the motion of our particle? Well, this is our acceleration at time t equals 10. Acceleration at time t equals 10. And since it's negative, we know our velocity is decreasing. Actually, I guess maybe a deceleration. Okay, so number 4. Let A of t denote the acceleration of the particle at time t. Is there guaranteed, right? So this means that we have to allow for holes in the graph if there are holes on not differentiable points. Although again, we already discussed up here, we were told that velocity is differentiable and continuous, so in this case we don't need to worry about that, but that is something to consider. Okay, are we guaranteed a time in the interval 0 to 12 so that acceleration is 0? And justify your answer. Okay, well, we already talked a little bit about what it means for velocity to equal 0, right? For velocity to equal 0, our position has to be going right and then switching and going left, or vice versa. It has to be moving left and then switching and moving right. The idea is that velocity changes from positive to negative or negative to positive. Because if there's going to be that change, there has to be a spot where it equals 0, remember? Think of your car. Okay, well, if acceleration is going to equal 0, then the same fact has to be true. We're looking to see, is there a spot where acceleration, okay, switches from positive to negative or vice versa, right? Switches negative to positive. Well, unfortunately, my table isn't an acceleration table. My table is a velocity table, and so I'm not going to be looking at velocity to see accelerations negative or positive, except that we have a relationship we know. Okay, numbers 8 and 9. If the acceleration of the particle is positive, or if the acceleration of the particle is negative, that's what we want, right? Positive and negative acceleration, we want to see them switch. Okay, then the velocity is increasing or decreasing. And so this is what I'm going to be looking for in my table, because my table has velocity, not acceleration. Okay, so I want to look at, in my table, is there a spot where my velocity goes from increasing to decreasing or decreasing to increasing? Let's take a look here. My velocity is -3 to 2, increasing, 2 to 3, increasing, 3 to 5, increasing, 5 to 7, increasing, 7 to 5, decreases. Okay, so that shows me right here, since it was increasing, my acceleration was positive, now decreasing, my acceleration is negative. The only way that can take place is for somewhere in this interval, acceleration has to be 0. And so yes, because our velocity changes from increasing to decreasing, which means acceleration changes sign. It goes from positive to negative. And since v of t is differentiable, which means there aren't any holes or any cusps that would in any way destroy our ability to guarantee, okay, since v of t is differentiable, there must be a point where a of t equals 0. Okay. If v of t wasn't differentiable, then we might have to allow for the spot, or the fact that there had been maybe a cusp there. If there's a cusp in our velocity graph or in our velocity table, then A of t wouldn't necessarily have to be 0. But because z of t is differentiable, a of t has to be 0 at least one point. On the back, we have problem B, which is graphical. We have the graph below represents the velocity v in feet per second of a particle moving along the x-axis over the interval from t equals 0 to t equals 9 seconds. Okay. Looking at this, I need to make note of the fact that this is a graph of velocity, v of t. Okay, so when I'm looking at this graph, when I'm reading this graph, when I'm answering these questions, I need to keep in mind I'm looking at velocity. And so I'm going to be answering all of my questions in terms of velocity's relationships to position and acceleration, right? This is velocity. Okay, so number 1, at t equals 4, is the particle moving to the right or left? Explain your answer. Okay, well, if I want to know where is the particle moving to the right or left, I'm going to be using these relationships here. If the velocity of the particle is positive, then we're moving right. Negative, we're moving left. Because again, I'm looking at velocity. Well, at t equals 4, I'm right here at positive 6. Right? Well, positive 6, velocity is positive, which means my particle is moving right. Because velocity at time t equals 4 is positive. Okay, number 2, over what time interval is the particle moving to the left? Well, if my particle is moving to the left, then that means velocity has to be negative. Okay. Well, where is velocity negative? Everywhere it is below the x-axis. And the interval that is below the x-axis is from 5, or t equals 5, right, to t equals 9, down here. Because again, velocity is negative on that interval. Okay, number 3, at t equals 4 seconds is the acceleration of the particle positive or negative. This is not an acceleration graph, so I'm not going to be looking just at the location of the point. I need to translate this question into terms of velocity, since my graph is a velocity graph. Well, if acceleration is positive or negative, what am I actually asking? I'm asking about v prime, right? Because derivative of velocity is acceleration. Well, what is derivative? Slope. So I want to know if the acceleration is positive or negative, is the slope positive or negative at t equals 4? When I look at my graph here, at t equals 4, my slope of my tangent line is definitely negative. And so my acceleration is negative because v prime at 4 is negative. Or you could say because the velocity at t equals 4 is decreasing. Okay, number 4, what is the average acceleration of the particle over the time interval 2 to 4? Show the computations that lead to your answer and indicate units of measurement. Average acceleration, we talked about this on the front, is the change in velocity over the change in time. Well, my time was 2 to 4. At t equals 2, my velocity is up here at 9. At t equals 4, my velocity is here at 6. So my average acceleration is 9 minus 6, which is 3, over 2 minus 4, which is negative 2. Velocity, we're told in the directions, is feet per second. And my time is seconds, or negative 3/2 feet per second squared. Okay. Number 5, is there guaranteed to be a time in the interval 2 to 4 such that v prime of t equals negative 3/2, and justify your answer? Okay, so I'm going to be looking here at my time interval 2 to 4, and I'm going to be seeing, well, is there a spot where v prime, where the slope of the tangent line of my graph could be equal to -3/2. Okay, so here's t equals 2, up and over to t equals 4. And there's two ways to answer this. One would be literally looking at the graph. When you're judging the slope of the tangent line, this interval 2 to 4 is made up of two lines, two linear equations. We can calculate their derivative the way we've always calculated slope, change in y over change in x. This interval from 2 to 3 has a slope of 3. And this interval from 3 to 4 has a slope of -6. There's literally no spot in that interval where the slope of our tangent line, if we were to draw it in, would be -3/2. And so you can see it just by looking at slopes of the tangent line. Well, the other way to answer it is to think about what we know about differentiability. Is there a spot between 2 and 4 where it's not differentiable? Because if it's not differentiable there, we aren't guaranteed a spot, right? We aren't guaranteed a location where our v prime is equal to -3/2. Well, right here at t equals 3, we have a cusp, which means that it is not differentiable. Velocity is not differentiable, so we aren't guaranteed a location where velocity equals -3/2. Even though we do switch from 3 to -6, and -3/2 lies in that interval. Because it's not differentiable, we aren't guaranteed that location. And so you can use either of those explanations. V of t is not differentiable. At t equals 3. And so we aren't guaranteed a location where v prime equals -3/2. Okay, number 6, last one for this one, says at what time t in the given interval is the particle farthest to the right? Okay, and so again, we're going to be asking ourselves here, what does our velocity help us see about our particle's motion? Because I want to know at what point is it the farthest right? Right here, if I look at my graph, picture your particle, right? From 0 up to 3 here, our particle is moving right. And then from 3 to 5, our velocity is still positive, so our particle is still moving right, right? Even though our acceleration is negative and so our velocity is decreasing, we're still moving right. We're just moving right at a slower velocity, at less of a velocity. Right here, though, at t equals 5, our particle switches direction and starts moving left. All the way to till 9. And so the place where our particle is the farthest right is going to be right here, right where it switches at t equals 5. Okay, last part here, we have problem C, which is our analytic. A particle moves along the x-axis so that at time t its position is given by x of t equals t cubed minus 6t squared plus 9t plus 11. So this is position. At t equals 0, is the particle moving to the right or to the left? Well, if we're wanting to find whether or not it's moving to the right or the left, that's a measure of velocity, right? It's moving right if velocity is positive. It's moving left if velocity is negative. Okay, we don't want to plug in t equals 0 into our position function, because if we do, the only thing that tells us is where our particle is at t equals 0. We don't know whether our particle is moving right or left from that point. We just know where it's located. Okay, so we need to find out, well, what is our velocity? And velocity is the derivative of position. So t cubed is 3t squared, minus 6t squared is minus 12t, plus 9t is plus 9, plus 11 is 0, because derivative of a constant is 0. And so now I can find my velocity at t equals 0. So we get 9. And so since velocity is 9, it's a positive, our particle is moving right And like we said, because velocity at time t equals 0 is positive. I'm going to go grab another pen really fast. Okay, number 2, we're asked at t equals 1, is the velocity of the particle increasing or decreasing? Explain your answer. Well, if velocity is increasing or decreasing, that's actually asking me what's my acceleration doing? Is my acceleration positive or negative? And again, the reason we know this is if we put t equals 1 into our velocity equation, that doesn't tell us what our velocity is or how our velocity is changing. Plugging t equals 1 into velocity just tells us what our velocity is at that time, right? Tells us our velocity is 4 feet per second or -9 feet per second, right? It gives us a measurement. It doesn't tell us whether we're increasing or decreasing from that measurement. Okay, so we need to go to the next step. We need to figure out what's our acceleration, because that'll show what our velocity is doing. Okay, acceleration is the derivative of velocity. Derivative of 3t squared is 6t. Negative 12t is negative 12, and derivative of positive 9 is 0 because it's a constant. And so now I can find my acceleration at t equals 1. It's negative 6. And so since our acceleration is negative, okay, our velocity is decreasing. And like we just said, because our acceleration at t equals 1 is negative. Okay, number 3, we're asked to find all values of t for which the particle is moving to the left. Okay, well you have the, I guess, choice in a way. You could plug in values of t to find where they are negative, but you're going to be plugging in a lot of numbers, and you're probably going to make a mistake or miss one or that kind of thing. So we're actually going to utilize a tool, a test that we used in Unit 3 called a derivative test, our first derivative test, which means we found our zeros and we put them on a number line and tested those intervals. The reason we're going to do that, okay, is because if we can find where velocity is 0, right, so here's our v of t is 3t squared minus 12t plus 9. We found that in number 1. If we can find where it equals 0, then the only option to the right or to the left of those times where velocity is 0 is for velocity to either be positive or negative. Right? Because if we found all the zeros, there's no way for it to be anything else. Okay, so we're going to go ahead and find our zeros. This one's a fairly easy one to factor here, so we're going to go ahead and practice that. And we get 0 equals 3t minus 3, t minus 1. So we know t equals 3 or 1. And that makes velocity equal 0. If you wanted to, if this wasn't an easy one to factor, if it showed up on the graphing calculator portion of your exam, you need to write this statement here. You do need to say that velocity equals 0, but once you've made that statement, you can plug your function in, 3t squared minus 12t plus 9, you can graph it, and then you can use your zeros tool to calculate your zeros. To the left, to the right, we get 3, and to the left, to the right, we get t equals 1. But you do have to make this statement that velocity equals 0. Okay, and so then once we found where our velocity equals 0, we can plug those on a number line and we can test these intervals. All right, when t equals 0, our velocity is positive. When t equals 2, for example, that's between 1 and 3, our velocity is negative when I plug 2 in here. And 4, my velocity is positive. And so where is my particle moving left? My particle moves left when velocity is negative, which is between 1 and 3. Okay, last one here. we are going to be finding what is the total distance traveled by the particle over the time interval 0 to 5. Total distance is found by taking the integral from a to b, in this case 0 to 5, of the absolute value of our velocity, which is 3t squared minus 12t plus 9. So then we go integral. Absolute values, 89s we hit catalog, ABS. 84s you'll hit math. Go sideways 1 to NUM, and then it'll be the first one, ABS. And then we can type it in, 3t squared minus 12t plus 9 dt from 0 to 5. And we should get 28. That is my answer.